So over the next, 40 minutes or so, Maxim and myself will cover some of the trends that we see in commercial vehicles, particularly around efficiency and emissions, some of the regulations that we see going on that are going to impact many of us in this particular industry. We're going to look at some best practices, what existing customers have been doing. We'll give you some hints, some tips, some things that we've learned, as well as a look at what some other companies are doing as well. We'll also provide you with a short demonstration on some important area of what we see customers doing and our software, and then finish up, like Eugen said, with some questions and answers. So hopefully that makes some sense for everybody. You know, right now there is a very large imperative around green efforts generally. Both the US and the European Union have noticed this. They've seen a need for action, in particular with respect to commercial vehicles, and specifically freight transport has been a particular focus of industry. If we look at what the US economy says, depends on trucks to deliver something like 70% of all freight in the US, and just a 1% fuel efficiency increase would save, well, you can see on this slide, right, 49 million Mercedes fuel tanks. That's quite a lot. That's just on an annual footing. The impact that trucks and other commercial vehicles have on our environment is huge. In addition, there's a tremendous amount of money to be saved. If you're a fleet owner or operator, the amount of money represented in the savings that can be achieved here is tremendous. So it's in everybody's interest, for a whole bunch of very good reasons, to make sure that the way we're transporting our freight, wherever that is being done so efficiently as possible. Now, to help that, there's a couple of programs that are going on, both here in Europe and also in the US. You can see from this slide that the Environmental Protection Agency, the EPA, has adopted legislation that aims to reduce greenhouse emissions not just by 1%, but by 40% by 2027. The EU is passing legislation right now to reduce emissions too, by 15% in 2025 and then up to 30% by 2030. So, of course, in order to meet those goals, we've got to act now. And, of course, not everybody is waiting. As I'm sure many of you are aware, one of our customers, we're proud to say, from MSC, Tesla here, is also doing this. Many of you have seen the truck that they've put out there, some very innovative designs, doing some very innovative things. So we've got a few companies out there doing something special. So it's up to all of us, though, to try to make this change. Not just one leading company, but all of us. Now, from MSC's perspective, we provide a lot of simulation software, and you can imagine there's a number of areas that we can help, whether it's drivetrain efficiency, electric and hybrid powertrain simulation, sensor and optical systems that typically go with some of the autonomous vehicles that are out there, electronics, cooling, right? Lightweighting, handling, rolling resistance, and of course aerodynamics, fuel efficiency, and the environment in which things are transported and in which people sit are all tremendously important. But there are a couple of focus areas that we need to focus on. When it comes to efficiency and emissions, some of our customers have done some research, and there are some major culprits. Drag, engine mechanical loss, rolling resistance be amongst the big guys, right? So from our perspective, we're kind of very proud at MSC because we have two of the major solutions to solving those problems. At a very simple level, we have Cradle, some industry-leading CFD technology that we can apply to this problem, as well as Adams, the world leader in multi-body dynamics. So if things move or there's fluids involved, we can simulate them. Not only that, we can couple these together in a rather unique way to provide a very rich view of a combined view of what is actually happening with respect to vehicle performance. So we believe we've got something special. And that's why we believe many companies are choosing MSC to simulate some of these things. So that's enough for the advert here. Let's have a look at some key technology. Right? Let's give you a demonstration of some of the key things that people are doing, particularly around that core problem. We'll focus in on the aerodynamics piece a little bit and have a look at what we can do with some key capabilities that we have here at MSC and give you some insight as to what some companies are doing, particularly around aerodynamics. So Max, are you still there?
Yeah, I'm still here.
Shall I pass you the ball and you can present?
Yeah. I'm waiting.
Excellent. Should be coming to you. I can see your screen.
Okay, perfect. So let me show you how easily we can handle one of the problematics you could face in order to reduce fuel consumption. As Keith said, CFD solution can provide a lot of information in order to reduce drag force, causing energy loss. So let me show you how we can deal with this problematic with our CFD solution. So this is the GUI of our solution. And here I will show you step by step the setup of a simulation and then how to extract from this simulation useful information for that. So of course the first step is about importing your CAD geometry. So for that you can use neutral files such as Parasolid, natives files, or so on. In this case I will just take Parasolid. But of course, depending on where you are in your project, if you are very upfront or if you are more advanced, we would recommend you to use different level of detail for your CAD geometry. If you are more in a design variation process, for sure we will advise you to use simple model, like the one I'm loading here now on my screen. But of course, if you are more advanced, if you are more looking for validation, we would recommend to put more detail in your CAD geometry. So let's try with this one here. So as you can see, I have my trucks with a few details, but it's a basic truck and trailer model here. Of course, this is what you get from your CAD software. But since we are dealing with CFD, we will also be interested about the surrounding of this vehicle. So for that, we can create a volume around this truck. So let's say, for example, something like this. Let's check. Yes, I think it's enough for this demonstration at least. So let's consider this volume of air surrounding the vehicle. And now the next step is about checking if the CAD data is clean enough or not to go till a mesh without any problem. Because, and this is a previous user of solution or simulation solution here talking, there is nothing more frustrating than setting up the whole simulation, and then at the final step, the mesh, you get a pop-up message telling you that you have CAD issues, so you need to go back to the CAD software to fix the issues, and then come back to the solution, the simulation solution, and then reset up once again. It means that you have lost your time on the first try. So here the good news is that at this early stage, you are able to check if the CAD data is clean enough or not to go till the end without any problem. So once you have checked this, we'll deal with the material that we want to assign to the different bodies here in the model. So in this case, it's very simple because we'll just assign a fluid property for the surrounding volume. So let's keep it simple here, air around the vehicle. Then we'll register region. So for us, region is one or group of surface that we want to clearly identify. It can be for applying boundary condition. It can be for meshing purpose. It can be also for post-treatment. So let me show you. For example, here, I will just register the sides, the road, the top, but also the vehicle itself. Let's say, for example, here, as a whole thing, this truck. Okay, that's it. And now I'm able to set up the simulation itself. So for the setup, we have this wizard, so don't worry, I won't detail each panel that you have here. I will just show you the main ones that can be useful in this specific application about aerodynamism. So here, the first panel, analysis type, is where you choose what you want to be solved during calculation. So for sure, in this case, we will be interested about flow calculation, and you can also go to advanced settings, for example, to choose the turbulence model that is maybe more efficient in your application. So the good news is that the default model here, SST K omega model, this is a default one, and it perfectly fits the need for the aerodynamism application. So we'll keep it this way. So still in a design variation perspective, I would say this default parameter can be fine. Of course, if you are once again on another level of detail, if you want something really detailed for validation, maybe you can use more advanced features such as porous media, for example, to really easily take into account the influence, for example, of the underhood. So here in this case, maybe the cooling system of your truck. So for that, you will just consider a resistive volume here, considering the flow resistance induced by this specific area for the airflow. So this is for the analysis type. Now let's speak about boundary condition. So here we rely on the regions that we have registered previously. So we can specify to the solver what's happening around our truck. So here in this case, on the side of our domain, we can specify, for example, if we know the velocity of the wind maybe acting on the vehicle. So for this, of course, we will consider the rolling speed of the truck itself. So let's say, for example, regarding the axis, okay, maybe we have something like 25 meters per second. It's a standard value for experimental characterization, for example. So this is for the rolling speed of the truck. But more than that, you also have to consider the natural wind speed, what we call crosswind, because it's not always in the vehicle path. So maybe, for example, let's do it this way. As you can see here, we can consider the rolling speed of the vehicle and then, in addition, a natural wind coming this way. So the interesting point is that maybe for experimental, you get several data coming from different wind direction. In this case, you can set up really easily all the range of wind direction that you want to test. So here I've put one value, but for sure you can really easily automate it so that with one setup of simulation, you can get a multitude of result sets corresponding to different wind direction. So this is for the wind here. Maybe on the top level of our domain, we'll just consider something like atmospheric pressure. For the road itself, we can consider that this will be moving according to the rolling speed. That's it. So this is for the boundary condition. Of course, you can also access to the, I would say, the numerical aspect of the solver, if you want to tune it a little bit or not. Once again, the default setting perfectly fits the need for this application, so it's a good news. Now let's talk about the output that we will get from the solving. By default, you will get pressure distribution, velocity of air, turbulence, a lot of useful information, but you can also ask for more specific results in your application. So in this case, for example, we can ask the solver to automatically calculate the force that will be applied on our model. So this is why we have registered here the truck and trailer as a region, because we can ask the solver directly to calculate the drag force applying on the vehicle. But of course, in this example, I consider the vehicle as whole, but you can for sure split your model into different areas if you want to look in detail about, for example, device that you want to put on your vehicle to reduce drag force, for example. So this is about the setup. Now let's talk about the mesh. So for the mesh, we do it in two steps. The first one, we will set the local mesh densities on the model. So for example, let's use something in terms of cell size, something between 0.5 and 1 meter elements. So let me show you a quick preview of what it means here. So don't worry, this is not the cell that we will use for solving. It's just a preview, as I said, just to get an idea about the coarse or the fineness of the mesh here. So in this case, of course, with this kind of cell, we'll miss a lot of accuracy, especially around the truck. That's where the regions can also be helpful here, because we can ask for specific regions or specific volumes a finer mesh. So let's say, for example, around the truck itself, I want something finer, like 2 centimeters element. I will just recreate this preview. So by the way, we get also an estimation of the number of elements. So we know if we are creating a monster or maybe a light simulation. And in this case, let me just show you here what we get around the truck. So as you can see, with these parameters, I get something finer around the truck, my main interest point in this application. So this is for setting up the local mesh density in the model. And now the second step is about the mesh itself. So for the mesh, we use polyhedral mesh at the core of the model. And near from the walls, near from the boundaries, we'll use what we call prism layer. This is something with a higher aspect ratio that help us to really catch the physics occurring near the walls. For example, here, near from the surface of the vehicle, we'll get huge gradients of velocity, of pressure, and so on. So to catch this physics, we will use this kind of elements. And then we can specify here the number of prism layers that we want here to use near from these walls. We can also rely on existing pre-configuration already saved in the program, but you can also access and tune your own parameters here. So you can access to any kind of parameters that you can imagine to check the quality and to control the quality of elements in your mesh. So let me show you here an example of mesh that we can use, especially in this case. So this is the same model of truck here. As I said, we have polyhedral mesh here at core, and what I just described here, prism layers. So in order to catch high gradients of speed or pressure here near from the boundaries. Okay. So at this point, everything is ready for calculation itself, and during the calculation, you will get a kind of log file like this one. And in this log file, you can find here the drag force that we have asked for the solver to output here. And you can monitor here the drag force, the total drag force applying on your model. So here on my vehicle. So this drag force is directly something that you can use to quantify and to check if your solution is aerodynamic or not. Of course, after the calculation is complete, you can access to the post-treatment itself, so like here. So we can check, for example, the pressure level on the truck itself or on the air. We can check all this pressure level. So high pressure level here stands for airflow resistance and energy losses. So we can check for this pressure. We can check also on low pressure level in the air, also standing for pressure energy loss areas. Let's come back here on the pressure themselves. And let's consider that we are in design variation. So maybe we have run a few different configurations of this truck rolling. We can easily compare directly different configuration here. So let's say, for example, in this case, we have a configuration without a cap and here with a cap. And we can directly check if this device is efficient or not here in terms of pressure applying on the truck. And once again, the pressure stands for energy losses. And thanks to this, we are able to check if these devices are worth or not. So this is completely the idea of design variation, to check if something is going in the right direction or not. As you can see here, for example, we have high pressure areas here and here. And thanks to this device, this fairing, this simple fairing, we have suppressed this area of trouble in terms of aerodynamism. So it's very simple here to check if we are going in the right direction or not. But more than that, we'll be also able to check directly and quantify the amount of benefits, if benefits, in the implementation of this kind of device. So as you can see here, you can directly compare from the first configuration without the fairing. We get an amount of force acting on the truck. And here, with the configuration including the fairing, we can see that here the force is reduced by something like 20%. And these calculations are really fast to run. For example, on an 8-core machine, one single calculation lasts something like 45 minutes. So as you can see, it's not a big deal. And in this, let's say, 1 hour, you are able to check if this fairing is worth or not in terms of aerodynamism. So I hope this presentation was useful. Please, I give you the hand.
Thanks, Max. Hopefully you can see my screen again. So a simple demonstration of a very interactive demonstration of what can be possible with something like CFD. You know, the sort of analysis there's a few hints and tips that Max provided, a few levels of automation that we provide. Obviously, relatively simple demonstration, and no co-simulation there. You know, we didn't do much in the world of optimization, for example, and we didn't do much in terms of, you know, automation that can be applied. We'll come back to those things in a minute. It's just a simple outline of what's possible. All right, so let's start looking at what real-world examples are out there from what real customers are doing. All right, so one of my favorite examples is actually from my Japanese colleagues with a company called Hino. Here they're doing truck and bus aerodynamics as well. And just like Max said, they're also doing a lot of drag, crosswind forces, that kind of work as well. But they're also looking at what's going on inside the vehicle, particularly around the engine and some of those other areas that were outlined at the start of this demonstration to improve the situation. Things like catalytic reduction, particulate reductions as well as the refrigeration systems themselves around these vehicles. Right? It's not just one thing that's going on. There's a number of things combining to impact the overall efficiency of these vehicles. And it's that kind of idea that Hino have embodied very well. So on one side of the equation, they've spent a lot of time looking at the processes that they have around the aerodynamics of their vehicles. Like Max said early on in the process, they're doing relatively simple design shape variations. Then, as their designs come into more focus, they're adding more and more detail and validating more and more. The designs up front are quick, simple, relatively dirty to get overall design intent working. Designs later on, obviously there to quantify specific design ideas. You can also see that particularly around those validation points, they're comparing back to simulation, to actual physical tests as well. Right, so that what they can do is reduce significantly the amount of physical prototypes that they do and correlate those together. The result is a pretty powerful one, right? In addition to simulating crosswinds and being able to understand different variances in geometry, they're also able to map out the drag coefficient by against fuel consumption for their prototype vehicles for different configurations of every vehicle that they have. That's pretty powerful stuff. Right, so this enables them to make design decisions before anybody's actually in production and try to address some of the key things that their owners are going to be looking for. Fuel consumption being a key one. Increasingly, it's going to be emissions calculation information moving forward. You can also see from this slide some of the correlation that they've got with their actual wind tunnel tests, 2 to 4%. That's pretty accurate. So really nice example of aerodynamics as well as some detailed examples around the engine. Speaking of engines, another example that I particularly like is from ISUZU. Here, ISUZU have embedded quite a bit of detail into the CAD solution themselves, choosing to take their standard processes and make those processes available to more designers and engineers and remove the restrictions around some of the usage of these tool sets. Some of them can be a bit complicated. So some of them, all of a sudden, with that, we're enabling regular design engineers to get access to these tool sets and start producing standard simulations again and again and again. You can see that they're turning around the simulations that they're doing much faster than they were before because the amount of preparation is a lot less. It's automated. There's that 50% reduction there. So being able to identify standard processes and then being able to automate these processes is really important. We can also see a whole bunch of optimization going on here as well. Both the water and cooling around the engine for the water jacket, obviously quite important for the efficiency of that engine, as well as the inlet and exhaust port configurations. Here, balancing the engine much more efficiently and but through the simulation of that detailed flow inside the engine. So here you can see some simple charts at the bottom right there showing how much more balanced the flow rates are across the different cylinders. Obviously, if an engine's balanced, it's going to be more efficient, right? So some really nice examples. Another great example that I like here is from a company called ACR. These guys do well, a number of important pieces of equipment for extended range electric vehicles. In this particular case, one of the world's smallest turbochargers. The demand for these is very strong. In this case, they're looking at delivery firms here where, fuel consumption is obviously high. We're talking about long distances, heavy loads, a lot of stop-go driving, right? All of that kind of conspires to make EV vehicles kind of challenging. So in this case, they're combining some of their existing technology with new tools and new technologies for micro-engine design there to extend the range of their electric vehicles. In this particular case, they're doing simulation, combining to figure out the efficiency of these components, and then producing these through additive manufacturing. So it's actually a really nice case study here, being able to produce slightly different, more complex designs than it perhaps would have done with traditional manufacturing processes alone. Another great example, and it's something I appreciate as an ex-HVAC engineer back in the day, is the fact that, well, at least with electric vehicles, there's a lack of a compressor. So something else needs to take its place, and with the increased noise, well, the increased perception of noise in particular, as well as the traditional effects around HVAC, we're having to do something different with respect to electric vehicles. So in this particular case, this company, CAE, is doing some great analyses of flow rates through the new technologies that they're introducing for HVAC, as well as introducing noise analysis. So a combination here, potentially a cradle, for example, with ACTRAT. Simple example there. Really nice example. All of a sudden, you've got quieter vehicles. All of a sudden, things like HVAC become increasingly noisy. It's obviously very fluid examples so far. We also see suspension, handling, rolling, as mentioned earlier, being important, right? A great example from a company in the US, right, who is simulating a new suspension in a different trailer configuration for a specific event in a matter of hours compared to the days or weeks that used to be required, particularly with physical prototypes. So they're evaluating all the different various tractor-trailer configurations against quite a wide range of operating conditions. For them, being able to minimize running and fuel costs, obviously very important for their operators. Another great example here, bringing together that engine viewpoint, is from Ford. Here, leveraging atoms in this particular case to optimize fuel economy with MBH. So being able to simulate different torque converter designs in the engine and the drivetrain to optimize those, make them as efficiently as possible, and really balance what's going on there in the system, particularly bearing in mind some of the converters that they've got going on. That way they can optimize torque, slip speed, and balance fuel economy and noise. Some really quite interesting use case in this particular example. Another great example that we've seen back in Japan in this case is what's been going on with Toyota and Panasonic. In both cases, great users of our solutions, particularly for CFD, and now getting together to combine to produce one of the world's largest providers of electric batteries. In this particular case, we're using a Prius in this case. This is from the Cradle User Group Conference 2014. If you drive a Prius, then you'll be glad to know that MSC helped simulate the Prius itself for the cooling system that goes around the electric battery. The battery itself is produced by Panasonic, another great user of Cradle. They're simulating the flow through the battery. So both through the battery and the cooling system around it, we've got quite a nice set of capabilities here to optimize the engine. So, all nice case studies. What are the lessons learned? One of my favorite papers on this particular subject is from the International Council on Clean Transportation in the US. They've derived something called the US Supertruck Program. I'll bring that up so you can see it. Here we've got some great detail around how the goals and aspirations that are trying to be driven into our environmental programs, but also they've got some very practical advice as to what different companies are doing. You can see here Daimler, Cummins, Navistar, Volvo, a couple of other great companies. You can also see the different effects and the focus levels that they're on. So transmission, rolling, weight, aerodynamics, right? And you can definitely see that aerodynamics is only part of the equation here. A good chunk of what these companies are doing, leading the way here for us, is across the broader swath of where engine efficiencies and where emissions efficiencies kind of happen. And it's got some great detail on that. So here you can see the breakdown of the energy that comes from the fuel to where it actually ends up, what happens in the braking area, drivetrain, loading, and so on. So it provides some really neat examples of where we can find that efficiency, some neat examples of good examples of specifics around what some of these leading companies are doing. In terms of engine design here, you can see some of the equipment and systems around the engine that has to be balanced, as well as aerodynamics, for example, and other leading things. So it's a really nice example, really nice white paper. If you haven't seen it, recommend it. You can see some great designs here with aerodynamics. Worth a read if you haven't seen that already. The International Council on Clean Transportation. Great paper. There's a number of other papers like this. This happens to be my favorite, which is outlined, because as you can see in this white paper, this particular chart here, it's not just about aerodynamics. However, I do lead the CFD here in EMEA, so it's not all about aerodynamics, but this particular paper does outline that one of the most cost-effective technologies that can be applied to this are those related to aerodynamics, in particular, the combination of truck and trailer. I know this is kind of obvious in hindsight, but we've got companies that make tractors and companies that make trailers. Unfortunately, in order to move something, it's the combination of these two that has to be considered. And it's actually the trailer that has a huge impact on the efficiency around aerodynamics and drag. And the combination of truck and trailer is obviously what needs to happen here. So you saw one simple example from Max here earlier with his very simple simulation where the roof fairing and the cab are more closely matched to the trailer. There was a small tractor to trailer gap as well. And you could also see a few other things going on, but that was a key point that brought out in a very simple analysis that Max did. You know, we can also see some other simple sort of rough guides here. The idea of what to do when iterating on designs versus validation is also a key one. You know, needless to say, we don't need to do a full-on transient simulation, for example, full-on time-based simulation at every point in the process. It's very possible to undertake simple conceptual simulations very simply, very quickly, to give some comparative direction right there in the design process. And you could see that at least one of our companies was trying to do that, trying to enable those design engineers to make decisions quickly and simply. You can see from other examples where they're using validation, where they do need to be quantifiable improvements. This is going to be quite a focus as more and more regulation comes in. I'm sure of those of you based in EMEA are perfectly aware of some of the tool sets coming in with the EU regulations. One of them requires that manufacturers start sharing some of these performance characteristics with users and operators. So all of a sudden, validation is going to get really important, right? Being able to provide actual figures of drag, either simulated or really tested, is going to get important moving on. We also saw some other examples here, right? So Max brought in a model that wasn't too large, you know, parasolid file if I remember correctly, but particularly when you get into the validation portion of things, the data that can be brought in can be huge. In addition to that need to automate processes and make things like that more simple, we have an ability and need to document processes generally. Right, so in this particular case, there's kind of two levels that we see. There's the documented process where somebody has just written that process down and we go through the process of simulation as a matter of rote. That's great. It's great that we have a process. It's great that people should know where that process is so they can get the simulation done, get access to the software that they need or if that's needed, and get them done. But we're also seeing increasing need to automate that. So one example where we did exactly that, right? And then we enabled many more people to do much more simulation when that's the case. In addition, processes like importing data and cleaning up models, which inevitably has to happen, gets a lot simpler. So as we start to document processes, the next logical step to get internal efficiency improvements and being able to simulate more is being able to automate them. Along with that idea, the idea of optimization. You know, in Max's case, that fairing that he applied, you know, that could change shape. That could be a subject of design variation. Right, so being able to understand different correlations and being able to understand different contributors to something like drag is an important idea. And that's a key part of increasing AI platforms, being able to mine data, understand how different physics interact with each other and being able to balance those things. A simple example earlier, right? So if we look at engines, increasingly they're being surrounded by more and more equipment to make them cleaner. Well, more and more equipment adds more weight to the overall engine. So all of a sudden, some of the improvements that we're getting from having cleaner engines is offset by the fact that they're heavier and therefore they need more fuel. Being able to make a balanced decision, a quantified balanced decision like that is part and parcel of tools like this, where we can start to understand how these things interact. And being able to do this automatically is increasingly important as well. So we saw at least one example of this where that was happening around the design variation on inlet ports. If you remember, they were using a tool like this. So that's an important learning as well. If you can, being able to optimize these things, being able to build on that automation that hopefully you've embedded, being able to build on the processes that we have is a key part of what we need to be able to do to keep improving. So some basic lessons learned here. You know, taking a step further forward, right, getting started, that's usually the biggest barrier. For us, we're quite proud of the fact that we have a whole range of solutions that can be applied to many of the problems here. Now, obviously, in this presentation, we focused rather heavily on aerodynamics and provided you a demonstration of that. But things like, engine performance, engine efficiency, tools like Adams, massive impact on that, particularly with VRES. Increasingly for autonomous ideas. Mark, from a structural perspective, really valuable. Nastran as well, from a lightweighting perspective, being able to remove geometry, make sure that, remove weight, make sure that tractors and trailers are stiff and rigid and as efficient as possible. Lightweighting materials, right, with Digimat, right, a whole bunch of solutions here that we believe provide some unique capabilities that can be applied broadly to these sort of problems. Yet, getting access to these can be a challenge. Buying every single one of these softwares and others from other people can be a challenge. Now, from our perspective, that's the reason we introduced something called MSC1. MSC1, we believe, provides a much smarter way to purchase software. What it allows you to do as a user is just buy a number of tokens. Those tokens can be used across most of our product sets when you need them, as you need them. So that enables you a huge amount more flexibility to use these tools when you need them, so that you're not just buying one set of tools, you're buying access to them all, and you can ramp up or ramp down your usage of these tools accordingly. So you can rent them for tokens for as little as a month if you need to, right? So all of a sudden, you can get access to the tools you need when you need them, and you can ramp up your access as you need it. We also talk a lot about how to get started with us as well, right? So we could, on the left-hand side here, just throw the software to you and let you get on with it. Most of our software does a great job of providing training in the box, so to speak, either as online courses or actually in the software itself. There's usually a great community, and obviously when you buy it, you get access to some smart personnel as well. But the challenge here is that most people's day job is not spent or shouldn't be spent learning software. So on the other end of the spectrum, there's the simulation services that we can do, right? We have a bunch of very smart folks with a whole bunch of experience undertaking simulations like some of the things we've just shown you. But the trouble is that that doesn't leave you, our customers, with the intellectual property that you need to drive your designs forward. So we don't particularly like doing that. Where we find the best solution is in the middle, something called a jump start. Here, after a simple briefing based on what you need, we'll give you some training based on that specific use case. The last day of that standard training is usually spent on your geometry, doing your particular problems and helping you solve that particular problem. And say over the next month or so, depending on what it is you're doing, we'll provide you with supporting days to help you get your problem solved. At the end of that period of time, typically it's about a month, we give you a report. Typically, we charge for training costs before you get stuck into the software and purchase it. So that jumpstart is tremendously useful. What we like to do is make sure that we're working on a real problem, not some contrived benchmark or some theoretical model. We want to provide value immediately. So having a real use case that you really need to solve is tremendously important. That way you get to leverage some of the simulation industry's most experienced team, and we do believe that. We've got a great satisfaction rating from our customers, we've got a whole bunch of experience, and a very high renewal rate and satisfaction rating across our overall customer base. Right? We are here to help our customers succeed. That's why I lead a Center of Excellence for CFD. So, all important ideas to help you get started. From our perspective, we believe that we've got some of the world's most trusted simulation tool sets, whether it's Cradle for CFD that we just shown you earlier, or Adams or Nastran, a whole bunch of very powerful tools that we believe can add real value to you, what you do, very immediately. So for that reason, we're challenging people, right? Get involved in a jumpstart, get us helping you, and we'll start helping solve some real problems. If you want to know more, you can ping us via the polling questionnaire, or you can send an email directly to myself or Yijin to start getting engaged here. So hopefully the last, 45 minutes or so have given you some insights, maybe some interesting insights to help you get started. I'm hoping to answer some questions, but that's it from us. Thanks for your time.